Very good afternoon to all dignitaries, guests, and delegates. It's welcome, ma'am. Now it's over.
Hello, am I audible?
Yes, ma'am.
Okay, thank you so much, Yogita. So let me, one just a second. This wavelet analysis has been honored by many awards like Haryana Yuva Vigamic Exchange Service.
Okay, thank you very much. Thank you, Dr. Nikki, for brief introduction. So first of all, and thankful to the principal of this college, GT. Actually, I will speak something about for solving the differential equation, or you can say partial differential equation. So may I share the screen?
Yes, sir, please share your screen.
Yeah, it's fine.
Yes, sir. It is.
Okay. So this is the topic of today's talk, wavelet analysis based scheme for solution of differential equation. And the main contents of these talks are why wavelets, why we use wavelet for solving the differential equation, or we can say in particular partial differential equation. And what is wavelet transfer is defined over minus infinity to plus infinity. Satisfies some property, so integration zero. Second thing, this is unity. Integration of the square means if you will do square here, so its integration will be. Condition is the admissibility condition, means Fourier transform of the wavelet function vanishes at the zero frequency. If any function, suppose I'm saying that fx this function is wavelet, so this will satisfy these three property, then this function become the. Don't go in the history, you can read easily, because just listen, this start in 1980s first time, and after that Jean Morlet used another wavelet, that is the Morlet wavelet, and after that Morlet and Grossman use one another wavelet in 1984 and published first time a research paper on the wavelet. After that, many wavelets come in picture: Debs's wavelet, Mayer wavelet, and many more. So these are some simple example of wavelet. First time wavelet are two type of functions. Sometimes continuous function, and some are just in time to some are the discrete wavelets. So these are examples of the discrete wavelets. Haar wavelet is the simplest one, so people prefer mostly by using Haar wavelets to find a solution of differential equation. Debs's wavelet and tool tree complex wavelet and complex wavelets. So these are some example of discrete wavelets. So this is a picture of Haar wavelet. If somebody is well known with Haar wavelets, so this is the picture of Haar wavelet. This is Debs's 4-tap wavelet. Means Debs's contain 4-tap, 8-tap like this. So this is 4-tap and this is the 12-tap picture of the Debs's wavelet. After that, these are some example of continuous wavelet, Mayer wavelet, Shannon wavelet, Morlet wavelet, and Mexican hat wavelets. Actually, not only these four, there are many wavelets available in literature for solving differential equation as well as to study the signal processing. These are some picture of the Mayer wavelet. This is the Mayer wavelet. This is the Mexican hat wavelet, and this is Morlet wavelet, and this is the Shannon wavelet, as I explained before this. So, as I told you that I will explain a method to solving the differential equation. Scale 2. There is also scale 3 wavelet, scale 3 Haar wavelet, but I will explain based on the scale 2 Haar wavelet. Scale 2, why it is called scale 2? Because this is Haar wavelet function is defined here. So we'll scale, for example, suppose j is equal to, you have used 4. So this become 2 to the power 2 and psi of this. So means that it is scaled by 4. If you will j is equal to, so it is called scaling parameter. And this shifting means this, as I told you that in picture of wavelet, suppose a wavelet start from here, then it will go here like this. So what is going on? If scaling parameter is same, but it is shifting the origin. So K work as a shifting parameter, or you can say translation index. You can say that. Okay. So these and any function can be used here. These are unknowns. These are unknown, and how to calculate these AK is unknown. So with the help of these property, this and this, we can compute this parameter. Okay. So simplest form of the Haar wavelet is this is scaling function. You can say before this I have used phi. So but for find over 0 to 1 interval means 4 are positive, 4 are negative. Okay, again 2 are positive, 2 are negative, rest are 0. Wavelet functions, and you can write this matrix. Yeah, as I told you that because what this is integration of Haar functions. This is the second integration, and this is x and dx. To solve this integration is if you are interested to solve differential equation using the wavelets, Haar wavelets. So these integrations are already. Now I'm explaining how to solve the differential equation using the Haar wavelets. So we have the differential equations. You considering the first or second order simple differential equation with the two conditions at 0. Suppose I'm saying alpha and y of 1 is equal to, okay, 1 is equal to beta. Okay, so this is the boundary value problem. Okay, so if you are from the numerical analysis background and you have used some method solving the differential equation, some method, collocation method. So what happens there? Generally, people assume it is 1 and say it is 2. I equal to 1 to n, and AI some function fxi. Means if you are using some collocation method, so assume y in this form and then differentiate this one time, so you will get it, and second time and put equation number one, so you will get the a linear system. And because AIs are unknown, so with the help of this linear system, after putting these y dash and y double dash in one and using the boundary condition, so you will get like this system, and you can solve this system to find these unknown AIs. So with the help of this system, you will find AIs and put AIs here, and you will get the solution. Generally this happens in every method. Okay, so but here is something different. In our wavelet, we assume the highest order derivative. What is the highest order derivative? Y double dash is the highest order derivative. So write this in the linear combination of AI is the unknown. So I running from 1 to 2m. Okay, as I told you that it will go up to 2m. 2m is even number, something 2, 4, 6, 8, 10, 12, like this. Okay, sorry. 2, it will be a 2 multiple. 2, 4, 8, 16, 32, 64, 182. 128. Okay, so and so on. So this is a solution. Assume solution in this form. Why we are doing this one? Because you can see that this function is not differentiable function. Okay, so that's why we cannot we cannot differentiate like the collocation methods, so that finite derivative. So we cannot assume, because I suppose you have assumed like this. Okay, and you want to differentiate this y dash. So this function is not differentiable, so you cannot find this differentiation. Sorry. So we go reverse in this method. R wavelet method, assume highest order derivative in form of R wavelets and integrate this. Integrate 2 with respect to x with limit, as I told you, that 0 to x. So means that when I will integrate 0 to this, y double dash dx is equal to summation I is equal to 1 to 2m ai, because ai are constant, so it will be outside from the integration, hix and dx. Okay, you can write t here because x is here, so this is no problem, it is a variable, just you can do it. So when you will integrate this one, so you will get what? Y dash of x minus y dash of 0. Okay, and this side summation I running from 1 to 2m ai. So I'm saying its integration, I already explained that the first integration of this is pi1 and second integration is pi2. So I'm saying pi1 of x. Okay, but this is unknown here, and this you can see that this and these are the boundary conditions. So I cannot apply here because this is y dash 0 here. Now again integrate, because I need what I need. I need y, because y is the solution, y dash. So y dash you will get here. So you can say I'm taking this that side. So this become, here is plus. Okay, again integrate. So when I will integrate, say it is 3. When you will integrate, so this will come, we will say yx is equal to y of 0 and plus, because this is constant here, x y dash of 0. I got what I got. I got y dash and y double dash. Now put in unknown. So you have to compute y dash and y0. Y0 is already, so but you have to compute this thing also, because this is the unknown here. So how to compute this unknown? By using the second boundary condition. I will use x is equal to 1 in 4. X is equal to 1 in 4. So what I will do, put x is equal to 1 in 4, we get, so we get y of 1 is equal to, what is the 4? 1 y x1 and so, okay. So alpha plus y dash of 0 plus summation I running from 1 to n ai pi 2 of 1. Okay, so this imply from here, because its value is what? Its value is also beta. So this become y dash 0 is equal to summation. This will go that side. So minus I running from 1 to 2m, sorry, 2m and ai pi 2 of 1 and plus beta and minus alpha. So this become y dash. Okay, so now using the value of y dash in in 4 and 3, because 3 is also this contain this and 4 contain this. So what I get, so y dash, now y dash x is equal to sorry, I forgot y dash even this, so I will combine. So this become beta minus alpha its value and minus summation I running from 1 to 2m ai pi 2 of 1 and plus summation I running from 1 to 2m ai pi 2 of x. Okay, so this ai contain this and this inter, so you can combine both of them. This plus summation I running from 1 to 2m and this become ai take outside and pi 2 of x minus pi 2 of 1. Yeah, pi2, you know already at pi 2 of 1 you can calculate from the that function which is already we have pi2. You can put its value is 1 upon 4m square. That's fine. And pi2x is the whole function. So this is finally. And yx is equal to what? Alpha plus x into. So x will multiply with all these things. So x beta minus alpha and it's again plus summation I running from 1 to, oh sorry, I think ai outside and pi 2 of x minus x and pi 2 of 1. So this become, we have this. So this is y dash, this is y, and y double dash is already I have assumed ai hix I running from 1 to. So now put all these things, put y, y dash and y double dash in 1, because we have used already boundary condition and everything. So for simplicity I'm just saying put for simplicity use boundary conditions are 0, means that otherwise you can take this, it is otherwise you can use alpha and beta as known thing, so you can use, but for simplicity I'm using here alpha is equal to 0 and beta is equal to 0 from 2m and ai pi1 x minus pi 2 of 1. Okay, and plus y is what? Y is again, y is this one. So alpha beta are 0, so only this ai summation ai pi2 of x minus x pi1 of pi2 of 1. Okay, and is equal to f of x. Okay, so now xj is equal to what? Sorry, I have to check that. What people use in hard wavelets? Uniform points analytics, but what is its value exactly? So I think 0.5 divided by 2m. I like this. Not confirm. I will confirm later. But this is the xj. J is running from j is equal to 1 to 2m, like this. Okay. So yeah, I think this is fine. So these are our points. So putting this and combine all these things, so this becomes summation I running from 1 to 2m, ai take outside, hixj and plus pi1 xj minus pi2 1 and plus plus pi to xj and minus xj, last one, this one xj and pi 2 of 1. Okay, this is equal to f of xj. You can see that when you will put j is equal to 1 to 2m, so this become matrix like this. Here is a1, a2 and a2m, and this side become f of x1, f of x2 and f of x2m. And this side, this matrix will be contain the element of these things. Okay, you know that this matrix already we have, this matrix we have, this matrix we have, and its value, as I told you, that comes from there. So this matrix become like this. This matrix, I'm saying that it is y, it is b, so this become a y equal to b. So, okay, what is your unknown? Our unknown are AIs. Yeah, you can say Y. So, Y you can calculate. As you know that this is the direct command in MATLAB. Use this and you will get AI from here. So, get AIs, but what is our solution? Our solution is Y. After getting AIs from here, so you have to put this AI in Y, this Y. Because this unknown, this is known, and this everything is known, so we will get the, actually there are many way because this was just one boundary. There are many boundary type, boundary problem means that for example if our boundary conditions are, this was Dirichlet boundary condition, Dirichlet boundary condition. If suppose our conditions are like mixed type, y of dash of 0 suppose 1 is equal to beta. So this is a mixed type. Yeah, Robin's, because this was just way how to use wavelets. So this is the parabolic PD. This is u dot means what? U dot is like this. You can say ut is equal to f of u dash and u double dash. Means that for simple example, I'm saying ut is equal to suppose uxx. This is the heat equation. Okay, and heat equation is a particular form of this one. So I just notation dot denote the derivative, partial derivative with respect to t, and dash denote the derivative partially with respect to x. So this is okay, and x belong to this interval and t belong to t minimum and t maximum. Obviously, initially t this is always 0 and t is maximum depend upon your problem. So with some initial condition, and these are some boundary conditions because here is 0, and so this is the explanation how to solve the partial differential equation. Yeah, you can say time dependent PD using the Haar wavelets. So as I told you that if I base, so total u dot double dash in form of AI HIX. Okay, so next what you will do, integrate this with respect to one time, and then integrate twice time with respect to x. One time with respect to, okay, as I told you that this is just notation. This in form a t to
methods to solve linear ODEs is not analytically solvable. So what we do two things. We can see the behavior of the solution of nonlinear ODEs using two methods, either numerical solutions or qualitative solutions. So now has given the a theory of Lyapunov to find the stability of nonlinear ODEs. And these are the chronology in development of Lyapunov theory. Okay, now we come to the definition. We know is the function d to Rn with the local ellipsis. Why I'm calling taking here local ellipsis? Because we need a unique solution. So we know we have studied in our previous courses that this type of differential equation will have a solution if this function has a solution of such type of differential equation. We need equilibrium point. Equilibrium point means there is no change. It means the derivative should be 0. Since the point at which derivative is 0, that is called equilibrium points. equilibrium point, and then if for every given epsilon greater than 0, if we find delta neighborhood of equilibrium point xc, suppose, and this is the initial condition of the solution. If you find this neighborhood, then your solution will be called within some particular bounded region. So this is bounded region of radius, suppose epsilon. In that case, we can say that the solution of this differential equation is stable. And when we call it asymptotically stable, it means that your solution after if time approaches to infinity, then your solution will be going to the equilibrium point. It will converge to the equilibrium point. So in that case, we call this solution is asymptotically stable. But we convergent does not imply stability. If you are saying asymptotically stable, so direct, if the solution is the exponential stability, and exponential stability, it is the most important stability, because if you find the exponential stability of any solution, then you will have also the rate of change at which rate your solution is converging to the equilibrium point. So it is a particular form of asymptotical stability. So this is this lambda is the rate of convergence. So if you find this exponential stability, then you will able to find a convergent of rate of convergent of the solution. So that's why we study exponential stability. So this is the pictorial interpretation. These are the solution from. Then in that case, we call asymptotically stable. And if you want to show that there is an implication, exponential stability implies asymptotic stability, because I also said differential equation is minus x squared. Then we can solve this. Fortunately, xt is equal to this. This is the analytical solution, and x of 0 is the initial equilibrium point. We can see that if you equilibrium point, we can see that if you put the 0, then this 0 will be the equilibrium. That's why it is converging to equilibrium points. In that case, we call it asymptotically stable. This is the Vinograd's equation. This is the counter example that with every convergence solution is fine, but it is in the initial condition from delta neighborhood. If you do this, then it is if we are free to choose x in there is a difference linear solution, linear equations that have an integral solution. So the first method is to study the stability of this kind of nonlinear differential equation is linearization. Suppose we have a equilibrium point of Taylor's expansion. So this linear equations, linear differential equation, and where a is at the equilibrium, maybe it is non-zero. So you can use translation and translate to the zero equilibrium point. So when we have this matrix, then in that case, this equation 6 is the linear differential equation. And when you have the linear differential equation, then you can say many things about the solution. Okay, so whether the solution is stable and not stable, it depends on the eigenvalues of this matrix. Okay, this is the first and the very simple method to deal about the stability and the symptotical stability and something like. Okay, this is the linearization method. So when we call the system is using linearization method, the system is stable or not stable. So as we said that, as I said that if you have that matrix using Jacobian differentiation, Jacobian matrix, then if the eigenvalues, real part of eigenvalues is less than 0, and all the eigenvalues if less than 0, then in that case we can say that the system is exponentially stable. It means then your solution is converging to 0. If at least one eigenvalue, the real part of one eigenvalue is not less than 0, it means it is greater than 0, then in that case the solution is not stable, it is unstable. And if at least one eigenvalue is, the real part of eigenvalue is 0, in that case your method, linearization method, is failed. We cannot say anything about the solution, whether the solution is stable or not stable. Okay, so if, for example, suppose we have then no conclusion using the linearization method, but we have the we have the answer for this case when a is equal to 0 when we use Lyapunov method. So suppose if you use Lyapunov theory, then suppose this is the Lyapunov function as corresponding to that differential equation. And if you differentiate it and this differentiation is less equal to 0, it means that your solution is at x is equal to x is also stable at x is equal to 0 when a is equal to 0. I have not introduced it about Lyapunov theory, but just for example, I will introduce it in the next slide. So if we take the Lyapunov function, then we can say that at x equal to 0, in the case of a is equal to 0, you design a Lyapunov function like this, and you don't get your derivative is not negative in every neighborhood. It does not mean that this equilibrium point will be not stable, because it means only that this function is not Lyapunov function for this differential equation. Then you will see for other equation, other Lyapunov function, and in that case, if again you will not get this negative part, then we will see for other. Okay, so this is only sufficient condition, not necessary condition. So now we come to the pendulum problem. So in that case, for that kind pendulum problem, we can design this Lyapunov function as energy function, kinetic energy plus potential energy. Then if we add this is the positive definite function. We can see that if we solve them, then then it will be positive definite between minus 2 pi to 2 pi from here to here. So we can say anything about whether equilibrium point, this equilibrium point, origin equilibrium point is stable or not. Okay, if we differentiate it, then we can see that this has a derivative is 0. For it means that this is a stable one, and also less equal to 0 for some other region. So it is only a stable, and also in this figure we can see that this looks like a stable. Your solution is not going to the origin. And this is the damped pendulum problem. Damped, it means it has a friction. So this is a differential equation of damped pendulum problem, and it is a equilibrium point. And if we design Lyapunov function like adding the energy function, like energy function, potential energy plus kinetic energy, then you see that this differential equation is positive definite in this neighborhood minus 2 pi to 2 pi. And if we differentiate it, then in this neighborhood it is showing that this will less equal to 0. It means that x is only stable. But if you are dealing with damped pendulum problem, then physically it is asymptotically stable because it has a friction, and it will, if you once it is called this is global asymptotically stability. So in that case, if we want to see the global stability, then it is not enough to Vx is globally PD and globally ND, negative definite. In that case, for using these three conditions, GPD globally PD should be positive definite, globally positive definite, and radially unbounded, and its derivative is globally negative definite. In that case, we can say that this equilibrium point is globally asymptotically stable. Okay, bounded, and the third condition is that derivative is globally negative definite, and as case we call it globally asymptotically stable. We have in that case this will be strictly less than. And now the definition is exponential stability. So for the exponential stability, these two conditions should satisfy. The first condition is the condition number 5, Is also assuring us about this if this neighborhood delta neighborhood is become Lyapunov function and k2 is equal to 1 and age equal to, this is strictly less than 0 in some region, so this is globally stable. So as we say that said that the for to see the rate of change, rate of convergence. So this is a feature of exponential stability. So, as we have, as I said that in the previous slide, the Lyapunov function is just a sufficient condition, not necessary. If you design a Lyapunov function and it fails, it means that the derivative is not less equal to 0. It means that Lyapunov, that equation, that positive determinant function is not Lyapunov function for particular differential equation. Then you will see for other type of other equation, other Lyapunov function. So this is the only sufficient condition. So when we say that your system is unstable, we have the sufficient condition to say the system is stable or not. But if we fail using that Lyapunov function, then when we say that your system is unstable, okay, so for that case, this is the Chateau theorem. Using this theorem, we can say that your system is unstable. Suppose we are not able to find Lyapunov function for a particular differential equation. So to show that the given the unstable equilibrium point, but using Lyapunov function, we can only say when we can only talk about stability, not instability, and whether it is unstable or not. Only stability, exponential stability, and asymmetrical stability. So using Chateau theorem, x1 derivative and x2 the system of differential equation, and this is the Lyapunov function. Then this is the region where we have find at this condition number 2. This equilibrium point is an accumulation point for Vx greater than 0. If we take Vx greater than 0, then you will find this set mod of x1 greater than the derivative of Lyapunov function is greater than 0. This is PD, this equilibrium point when we fail using. So these are the conclusions. If we delta neighborhood and negative semi-definite in delta neighborhood, in that case, 0 is only a stable, okay, and not a necessary condition. Okay, any queries?
Okay, so sir, I have a query. Uh,
Ah,
Sir, for this Lyapunov function, that is, there any particular method to find one, or it's like we have to just see the conditions and we have to like hit and trial method to find
uh,
that particular.
it is hit and trial method because Lyapunov function is you have not a particular way to design Lyapunov function corresponding to given differential equation. You will
Okay.
design it based upon a function just as the energy function of this pendulum problem will be the Lyapunov function, okay, energy. So if we deal with mechanical and electrical problem, then energy of that problem is your Lyapunov function. But in other cases we have not any issue much for.
And now over to you, Yogita.
Thank you so every participants. Please wait for few. am certain that everyone is satisfied with the learnings they gained from this workshop. Okay, so at this juncture, on
लाभान्वित हुआ है, उन्होंने इस चैलेंज को स्वीकार किया और उन्होंने इस कार्यक्रम को ऑर्गेनाइज करने में अपना समस्त योगदान दिया। हालांकि
now it's over to you, sir.
Yogita, am I audible?
Yes, yes. Yes, sir.
Okay. Dear participants, on behalf of convener of this workshop, I wish to thank each participant of this workshop, all the invited speakers on stability and Kumar Singh, BHU on stability and
understand operations must have been of very high level, and I wish if I would have got the opportunity to attend this workshop, I would have considered myself a lucky person. So I once again congratulate Dr. Rahul Maurya because this is really an excellent
lecture from you also. So that's why now over to Nita, please.
I'm audible.
Yes,
My voice is clear or?
yes,
Okay, thank you, Yogita. Respected our chief guest, Dr. Pragesh Agrawal, Director of Institute for Excellence in Higher Education, Bhopal. Our principal, Dr. Sudhir Kumar Khare sir, and Dr. Chitra Prabhat, IQSC coordinator, and invited speakers and all the participants. Myself, Dr. Santosh Kumar Singh, Assistant Professor, Government Tilak College, Katni, for taking time out and joining with us. My sincerely thanks to all the invited speakers for taking out time and joining with us. I also would like to thank Sudhir Khare sir and our IQSC coordinator Dr. Chitra Prabhat ma'am for imaging such a wonderful and informative international workshop in their research. Once again, I am thankful to all the directly and indirectly involved in this workshop and indirectly involved in this workshop. I ensure that our college will again organize such type of workshop for research purpose and for student.
thank you so much, sir. Okay, so this concludes the workshop. Thank you so much all for attending. We hope